Hello, everyone. Good morning or good afternoon. Welcome to the new event of the ESO Hypatia Colloquium, Hypatia Colloquium 2022. This is, I remind you, this is a series of talks dedicated to early career scientists, and we are very happy to give this opportunity to bright student, early career student, to give to show us the science that they are doing. This is just a very technical point. As usual, please be reminded, this is mostly for people that are connected via Zoom, that this event is live broadcasted on YouTube. And if you are uncomfortable with that, you can leave please leave the event, and then you can still join and follow the event live on YouTube. The two speakers will have 30 minutes of slot each, and at the end of the talk, it will be possible to make questions, of course, ask questions or make comments using the live chat on YouTube, or you can directly talk to speakers on Zoom by raising your hand, and then the chair will give you the word to talk. And please remember to always go to our webpage where the program is available, and there you can click on the title of the talks, and then you can download and have a look at the CV of our speakers. And with this, I will jump immediately to the presentation of the speaker. I have the pleasure to chair one of the sessions of today, of one of the speakers of today, Andrea Botteon, while Victoria Fawcett will be chaired by Paul Lowe, who is an ESO student who kindly support us today and will be co-chairing with me the event. Thank you, Paul, and thank you for being here today. So let me straight go to the introduction of Andrea. So Andrea did the PhD in Bologna. Basically finished the PhD in October 2018, and then after less than 1 year postdoc in Bologna, he moved then to Leiden Observatory, where he's doing as a postdoctoral researcher, where he's currently working. He's an expert of non-thermal phenomena emerging galaxy cluster. And as a matter of fact, today he's going to tell us about the most giant radio structure in the universe. So looking forward. So first of all, congratulations. As for every other speaker, congratulations, because I want to remind that the speakers are selected after a very competitive selection process. We have the large number of applications, so congratulations, and looking forward to hear about your science. Please, Andrea, you can take over.
Thank you, Giacomo. Thanks to the organizer also for this opportunity. And yes, today I'm going to talk about the most giant radio structures in the universe. And I would like to start my presentation with an image from numerical simulations of the universe at the present epoch. This image in particular is taken from the U2 simulation, which is the largest numerical simulation run to date, and shows the distribution of dark matter in our universe. As you can see, the dark matter is distributed in filaments, and there are regions in our universe that are underdense, the so-called voids, and there are regions that are overdense, that are called galaxy clusters, that are the subject of this talk. And galaxy clusters are the most massive gravitationally bound system in the universe, and they can reach masses up to 10 to the 15 solar masses. This is the status of the universe at the present epoch, and is the result of a progressive assembly of structures that occurred across its entire lifetime, as you can see in the image on the bottom. So structure formed across cosmic time, forming very massive systems. As my talk is on observation, I want to show you how a galaxy cluster actually looks like. In optical, as the name suggests, it is composed by hundreds to thousands of galaxies that are bound together by gravity. And despite the large number of galaxies, they constitute only a few percent of the total mass of a cluster. The majority of a mass in a cluster is in the form of dark matter that we cannot observe directly, but we can infer from lensing studies. The remaining part of baryons in clusters are in form of the intracluster medium, or ICM, which is a hot and tenuous plasma which permeates the entire cluster volume on megaparsec scale and that it emits in the X-rays via thermal remonstragung. There is another component in the ICM that is due to non-thermal components that are basically relativistic electrons and micro-Gauss magnetic fields that are also spread over the cluster scale, and they are reported in red in this image. As is the main subject of my presentation, I want to discuss these radio structures into more detail, showing you, for example, the case of a nearby coma cluster. So this kind of diffuse radio emission in a cluster have been divided mainly in two classes: radio halos that are centrally located diffuse emission that have a morphology that roughly recalls that of a thermal X-ray gas. They are unpolarized and they trace turbulence in the intracluster medium. At the periphery of cluster, we might find some elongated sources that are called radio relics, and that shows a high level of polarization, and compared to halos, they are only found in cluster outskirts. In contrast with halos, relics are associated to shocks in the intracluster medium. So as you can see, halos and relics are related to turbulence and shocks. So who generates these dynamical motions? Well, shocks and turbulence are naturally generated during the formation process of galaxy cluster. Indeed, when galaxy cluster collide, these motions are generated in the intracluster medium. And cluster mergers are very energetic events. They are actually the most energetic events in the universe since the Big Bang, and are able to release up to 10 to the 64 erg of energy in the ICM. And this energy is dissipated by shocks and turbulence, mainly in heating the gas, in the heating of the gas, but also in part into acceleration of particle and amplification of magnetic fields. And these are the non-thermal emission that we see in the radio band. So just to give you a schematic view of the formation processes of halos and relics, as I mentioned, when a galaxy is relaxed, so its X-ray morphology is regular and circular, we do not expect to see radio emission on cluster scale. But when clusters collide during the formation process, shock fronts are driven into cluster outskirts and are able to accelerate particles, generating this giant emission that we call radio relics. Instead, in the cluster center, turbulence is injected in the ICM, and this generates what we call radio halos in merging systems. As these radio emissions have steep synchrotron spectra, it means that they can better observed at low frequencies. That's why LOFAR and the LOFAR 2-meter sky survey, or LOTS, are two ideal instruments to study these kind of objects. So LOFAR is a telescope that is built mainly in the Netherlands, but is a station that are spread all over Europe, that is currently surveying the entire northern sky with unprecedented level of resolution and sensitivity in its operative frequency band. For example, here you can see the comparison of sensitivity and resolution of LOTS compared to other survey. LOTS is exploring an unexplored region in this plot, and this means that it's very sensitive to study diffuse radio sources in cluster, and it has the potential to detect many new radio halos and relics, and also new kind of sources. Indeed, one of the objects that I studied a few years ago with LOFAR and with LOTS is this system, which is called the Abell 1758, which is a double galaxy cluster. It's a galaxy cluster composed of two galaxy clusters, Abell 1758 North and Abell 1758 South. These two systems are bound, gravitationally bound, and form a premerging system, meaning that they are about to merge one against the other. What makes this system very interesting is that the two subcomponents, so Abel 1758 North and Abel 1758 South, are both massive emerging systems, meaning that they are undergoing their own distinct measure by their own, meaning that this system is emerging system taken alone, this system is emerging system taken alone, and together these two systems are merging each other, meaning that we are looking to a very rare case of a quadruple merger. And in addition, the two systems have a very high mass 500 greater than 5 to 10 to the 14 solar masses, meaning that we might look at maybe the most massive cluster pair known to date. So the interesting thing is when we have, you can see is when we have observed this cluster pair with LOFAR, and this is the image that we obtained in 2018 using LOTS data, so the data from the LOFAR 2 meter sky survey. So the two clusters host two giant radio halos. The northern radio halo was already known, is a very giant halo with a size of 2 megaparsec, and the emission in the southern system was reported for the first time thanks to the new observation that we used. We found a radio halo and a radio relic. But what is most interesting is that in 2018, we found the tentative evidence of a bridge of radio emission that is connecting the two galaxy clusters, that is reported here with these gray contours that denotes the 2 sigma level emission. So of course it's a 2 sigma level detection, so it's not very strong detection, but it's very interesting because it would prove that we are detecting radio emission on very giant scale, greater than 2 megaparsec, connecting two galaxy clusters. And this is something that we have never observed before. In addition, as I said at the beginning of my presentation, we expect to see radio emission in merging system. Instead, here we are seeing emission between two pre-merging galaxy clusters. For this reason, we run a deep multi-frequency observation of this cluster pair using observation from 50 megahertz to 1.5 gigahertz. And these images are reported here on the left. And these images confirm that the bridge is detected at least at 150 megahertz. So we have confirmed the bridge. In the other frequencies, we don't really see a clear detection. We see some patches at 50 megahertz and 380 megahertz of the bridge. In particular, there is a small patch at 50 megahertz that is detected above the 3 sigma level. And if we measure the spectral index between the 50 and 150 megahertz image, we would get a very steep spectral index for this portion of the radio bridge. This is, of course, very tentative because it's derived in a small portion of emission, but it's just that this emission might be the steep spectrum. And this is very important, as I will show you in a few slides, because it might tell us something about the origin of the radio bridge. What we were able to do is to compare the radio emissivities of the diffuse emission in this cluster. And the radio emissivity is basically the radio power emitted per unit volume. And in this plot, you can see the emissivity for the 4 radio sources, so the 2 radio halos, the relics, and the bridge, as a function of frequency. At 144 megahertz, where we detect all the source, we see that the radio bridge has an emissivity that is at least a factor of 10 below that of the 2 radio halos. And this is proving that we are starting to explore radio emission from basically an uncharted territory of low density environments. Sorry. In the meantime, another bridge connecting other two pre-merging galaxy clusters was reported, again with LOFAR observation, and this is reported in the image on the left. This bridge is also another giant emission that is extended for about 3 megaparsec and is connecting the clusters Able 401 and Able 399. And together, these two bridges are the only two detected to date, and they represent the most giant radio structures observed in the universe to date. Of course, as I mentioned, one might wonder what's the origin of these bridges, as they are new kind of sources. And for that reason, now there is an ongoing theoretical investigation of the processes that might lead to the formation of these structures. And at the moment, there are two proposals. One advanced in 2019, and in this proposal, there are the weak shocks that are generated in the region between the two galaxy clusters as soon as they collide. These weak shocks accelerate seed electrons that are present in the region between the two systems, generating what we see as a form of radio bridge. And this scenario has two main predictions. One is that the emission should follow the shock surfaces, and then the radio bridge should look patchy in structure. Instead, in a more recent model, the turbulence is responsible of the formation of radio bridge. And here, with numerical simulation, Brunetti and Bazza showed that the turbulence generated in the compressed gas between a pre-merging galaxy cluster is enough to amplify the magnetic field and reaccelerate particles in order to produce detectable level of radio emission between the two systems. This model has two strong implications. One is that the spectrum of the radio bridges must be steep, and the other is that the radio emission should be volume filling. This is due to the volume filling nature of turbulence. The interesting thing is that for Able 1758, we had enough signal to check at least some of these expectations. And as I mentioned, we have a tentative indication of a steep spectrum radio bridge. And from the comparison between the radio and X-ray signal in the region between the two galaxy clusters, we found that the two components are correlated, and they show also similar fluctuation in surface brightness across 4 transversal slices taken across the bridge. This might suggest that the emission is volume filling. So overall, our results on Able 1758 might suggest that turbulence might be responsible for the formation of these radio bridge. But of course, this is really a very recent topic. So theoretical observation, theoretical speculation are still ongoing. Also, from the observation point of view, there are other investigations because we have detected 2 radio bridges, and one might wonder if there are others. And that's why we also observed another pair of galaxy cluster with LOFAR and X-ray observation. And this cluster pair is the Lyra complex. That is composed by RxJ 1825, which is this system here on the left in the XMM image, and CISA 1824, which is this system here. These 2 clusters are in a pre-merger phase, and this system has some similarities to Able 1758, but also some differences. Indeed, this is a system that has a lower redshift, it is less massive, but it has a similar mass ratio between the 2 components compared to Able 1758. So these 2 images on the left are the LOFAR images, and this is an high resolution image, this is a medium resolution image. As you can see, we can see some diffuse radio emission located at the center of RxJ 1825, and this is a new discovered radio halo, which is already a cool discovery. that highlights how these low-for observation are able to detect these kind of signals. However, in the region between the two clusters, as you can see, we don't see levels of diffuse radio emission. This is true even when we image the cluster at very low resolution, so we increase the signal to noise of low surface brightness emission. So despite the fact that we don't see a radio bridge connecting these two systems, we found that the radio halo in RxJ 1825 has a low surface brightness extension extended toward the southwest direction. And as you can see, this extension in radio, reported with the radio contours, is following the emission, the extension that is observed in X-rays. And indeed, there is indication both from the X-ray and the optical analysis carried out by two other papers that this region of the system is dynamically active. And actually, there was a group that interacted with this system in the past. And this group is now located in the southwest outskirts of the system. And we speculated that the motion of this group generated turbulence in this region that powered the radio emission. And the presence of the group, as I mentioned, is confirmed both by the X-ray analysis and also from the optical structures observed with this bubble plot, so optical analysis. So as for the case of radio bridges, detected low surface brightness extension of radio halos in cluster outskirts is very important because we are proving magnetic field amplification and particle acceleration at very large distance from cluster center, something that is very important and new in this topic. Indeed, in my last slides, I would like to talk a bit more about cluster outskirts, using a figure that I showed you at the beginning of the presentation. So I mentioned that the radio halos and relics are, yes, giant radio sources. They cover megaparsec scale. However, they have been used to probe what is the inner region of cluster. In the simulation, as you can see here on the right, the turbulence and shock and the shocks generated in cluster merger dissipate energy on much broader scale. This circle of diameter 1 megaparsec is just this circle in the simulation. As you can see, there is a lot of kinetic energy dissipated in cluster outskirts, and in principle, these cluster outskirts are unexplored to date because we can observe only halos and relics. However, if turbulence and shocks are able to dissipate enough energy in cluster outskirts, with very deep radio observation, we might have the hope to detect the radio signature of the relativistic electrons and magnetic fields in the very far outskirts of systems, of galaxy clusters, something that is expected by simulation. That's why we wanted to do a very deep observation of a galaxy cluster. And for this reason, we choose Able 2255, which is a very spectacular system that was known to host a radio halo and a relic, plus a number of interesting detailed radio sources. And in 2020, we published the LOTS observations of the observation from the Low-for 2 meter sky survey using 8 hours of data. And this is the very nice image that we obtained 2 years ago. But now we have observed this system and reduced the data for 72-hour observation at 150 megahertz and 72-hour observation at 50 megahertz. And this is what I'm going to show you in a second. I just want to anticipate that this system will be also observed even further in the future, reaching a total of about 300 hours at 150 megahertz by the end of 2023. But let's focus on these very deep images that are these two. So here on the left, you can see the LBA image at 50 megahertz, while on the right, the image at 150 megahertz. These are the resolutions and the noise of the two images. If you are not familiar with radio observation, I can just tell you that these are very impressive sensitivities and resolution at such low frequencies. And these sensitive images are allowing us to detect a faint envelope of radio emission that is embedding the entire galaxy cluster and all the structure that were already known. And this is highlighted by these red crosses. Check the scale bar here on the top right. This is 1 megaparsec, meaning that the emission from the bottom to the top of the image is covering a projected linear size of about 5 megaparsec, or 20 megaparsec square in projected area. And just to give you an idea of the sizes, of the size of this emission, I want to show you a composite image. So this is the cluster as seen in optical. This is the X-ray emission from Rosat that is covering the megaparsec scale. This is what we have observed with 8 hours in the past. And this is what we observed now with very sensitive observation, this glow of emission that is surrounding the galaxy cluster and is extending up to and beyond R200, which is basically the viral radius. So I can't go much into detail also because I'm running out of time about the implication of this discovery, but I can just tell you that from this observation, we have understood that the turbulence and the shocks operating in cluster outskirts are able to accelerate particles and amplify magnetic fields efficiently, even at such large distances from the cluster center. And these are unexplored territories for cluster science. So let me summarize. So diffuse radio sources, I talked about diffuse radio sources in galaxy cluster that are probes of micro-Gauss magnetic fields and cosmic ray electrons in galaxy cluster that are spread on megaparsec scale. I talked about radio halos and relics that are sources connected to cluster mergers, and in particular to the turbulence and shocks generated during the collision between galaxy cluster. As these sources have steep spectrum, they can better observe at low frequencies, so LOFAR and the LOFAR surveys are ideal tool to study this emission. I reported the discovery of giant radio bridges connecting pre-emerging galaxy cluster. This is very important because these sources have 2, 3, 4 megaparsec extension, and is proving, and they are proving that in order to generate radio emission, we don't need very energetic merger events. The shocks and turbulence generated in the pre-emerging phase is enough to produce detectable level of radio emission. But of course, the origin of these bridges is still under debate. Then I talked about table 2255, which was chosen to be the LOFAR cluster deep field because it's simply the most complex system that we have observed to date with LOFAR, and the very deep observation shows the presence of a giant envelope of radio emission that is extended out to the viral radius. Both the discovery of radio bridges and the giant envelope in table 2255 are very important because they give us the possibility to study the acceleration mechanism and the amplification of magnetic fields on unprecedented large scales in the large scale structure of the universe. So the bottom line message is that we are moving further away from cluster center, and the hope is that in the future, with future instruments such as SKE, we might be finally able to detect the radio signature of the cosmic web that should glow on even larger scales. And that's all from my side. Thank you for your attention.
Great, and thank you very much. Very, very interesting. A lot of really exciting results. So we can open now the floor. We have a few minutes, 3 or 4 minutes for questions. So we have already, while people on the chat can raise their hand, we have a question on the chat from YouTube that I'm going to read it as it is written. Then let's see if you can answer the question directly. You can also read it if you want later. But anyway, it's from Nick Samaras. Hello, thanks for the talk. What happens if we neglect dark matter halos? Are the bridges connected to the model? Lambda CDM has been falsified. So this is what the question says.
Well, I'm talking about emission from baryons, actually, because we are looking. I mean, the radiation comes from electrons that are radiating into magnetic fields. So I am not sure if this question is related more on the implication of dark matter on the large-scale structure of the universe.
Yeah, I guess it's more, exactly, related to the modeling of such a. But maybe if you want, you can, since there is a contact, you can maybe, if you want to more clarification is on the chat, you can answer back, and then maybe there will be, or Nick can also explain a bit better, more details.
Have a look, sure.
Yeah, thanks. No, I have myself a question. I mean, I'm not in the field, but I found it very fascinating, the detection of such bridges. And I was wondering, so you show the case in which you told us this is very new, okay, this was never detected before, and then you showed us a case in which there is this, let's say they call it two clusters that are on the way to interaction, but there is a radio halo in that case. There is not a bridge, but a radio halo. So I was wondering, is it then expected that the two, well, the first question I have, so the radio, these bridges that were never theoretically predicted, whether this was never predicted before somehow. And the second question is that then you think the presence of bridges and radio halo or bridges is they are competitive physical processes. So if there is or just different stages of the emergence, basically.
Yeah. So bridges were not observed as we have. At the moment, so bridges between pre-emerging galaxy clusters. This is something new.
Okay.
There were some clusters where we saw some radio emission, and this was reported as radio bridge. But you know, bridge is a flexible word. As I intend, radio bridges between pre-emerging galaxy clusters is something new, and it was not investigated by simulations or theoretical investigation. Indeed, the first two works are this one. Okay. So the Govoni were proposed that shocks are responsible of the formation of the radio emission, and the Brunetti and Vatsa, where turbulence is expected to be responsible of the radio emission. And in this sense, to link to your second question, yeah, you see the main actors are the same, because also for radio halos and the relics, that were sources that were known since 20 years or more, turbulence and shocks are responsible were known to be responsible of the generation of this radio emission. The thing is that, yes, here the actors are the same, so shocks and turbulence, but they are acting in different regimes, because the region between galaxy cluster is a very low density environment compared to cluster cores, where we do see radio halos or radio relics in cluster outskirts.
Okay. And sorry, thank you very much. I have a very last question. If you go to slide 29, I think it's 29. Yeah, exactly. So this is, you showed this as this profile, and you said this is what we do indeed expect for turbulence. But I was wondering, what do you, because again, it's from a completely not in the, someone is not in the field. So which kind of profile would you expect in the case of shock?
No, yes. So the thing is that if the radio emission comes from turbulence, the turbulence has a volume filling nature because it's basically filling the entire gas. And the gas emits in the X-rays. So X-rays and radio emission should be correlated.
Okay.
When you have instead an emission that is powered by a shock, the shock is a region well located in the space. So you don't expect to see a correlation between radio and X-ray emission.
I see. Very, very nice. Thank you. Very clear.
Thank you.
Thank you very much. Okay, I think we can now thank you, Andrea. Congratulations. And now we can move to the next speaker. Thank you very much. Paul, the floor is yours.
Thank you. So, hi. So, it's my honor to introduce the second speaker, which is Vicky Fawcett. And she's actually doing a PhD, final year PhD in University of Durham. And also, she recently got a postdoc in the University of Newcastle. So I would first let Vicky, you share the screens, and then I will also pass the stage to Vicky to talk about her title, which is Why is Color Special? Fundamental Differences Between Red and Blue Quasars. So the stage is all yours.
Great, thank you. So yeah, hi everyone. My name is Vicky. I'm a final year PhD student at Durham University. So it's my great honor to be here today and talk to you a little bit about the work that I've been doing throughout my PhD on red and blue quasars. So just a little bit of background. Quasars, also known as QSOs, are extremely luminous types of active galactic nuclei. And the majority of quasars have very blue optical colors, and this is typically due to an unobscured view of the accretion disk. However, there's an important fraction that show much redder optical to infrared colors, and these are what we refer to as red quasars or RQSOs. And we think the red colors indicate that the accretion disk is obscured by some amount of dust. But whether this dust is due to an inclined dusty torus or a phase in the evolution of quasars has been debated. So here are the two main scenarios for red and blue quasars. On the left, we have this orientation model, and this is similar to the unified model of AGN, where here I have a blue quasar that has this unobscured view to the accretion disk. And then you can imagine a red quasar having a grazing angle through this dusty torus structure. So in this scenario, a red and blue quasar are intrinsically the same object. A red quasar is just slightly more inclined. On the right is this evolutionary scenario where red quasars may be a phase, potentially a younger phase, in the evolution of quasars or even galaxies. And this little comic strip I've taken from a press release that followed a former PhD student at Durham University, Lizelka Clint, her 2019 paper. And this is just one toy model that we could think about, where we start with merging galaxies that produces a lot of star formation. And then this ignites a quasar that's very dusty, which is our red quasar phase. And then through jets and winds, we blow off the dust and reveal this unobscured blue quasar, which might then eventually run out of power and become just a normal type galaxy. So at Durham, we've been really interested to try and distinguish between these two different scenarios. To do that, we've mainly used the Sloan Digital Sky Survey, SDSS, quasar catalogues, and the majority of the work I'll show is from the DR14 catalogue. So to select red quasars, we select them as the top 10% of the optical G-I color distribution. And we do this in a redshift dependent manner as shown as this by this plot here. But importantly, what our group also does is select a typical or control sample in a consistent way, which is what a lot of other red quasar studies or obscured quasar studies often don't do. And we do this by selecting the median 50% of this G-I distribution. And again, the majority of work I'll show, we also match in redshift and luminosity to take into account these effects. So all this work kicked off, like I've already mentioned, in Lizelka-Klint's 2019 paper, where she found fundamental differences in the VLA first radio properties of FDSS-DR7 red quasars. So VLA first is a radio survey at 1.4 gigahertz and 5 arcsecond resolution. So I'll just mention the two key results from her paper. First of all, we find a factor 3 higher radio detection rate in the red quasars compared to these typical blue quasars. And just to note, in this former study, Lizelka also included a blue sample, which was the bottom 10%, but we found very similar properties between our blue and control. So in the later studies, we dropped the blue sample. We also find this enhanced radio emission has a preference for faint or compact radio counterparts. So faint meaning we can't really tell anything about the morphology, they're too faint, and compact meaning that they're unresolved at the resolution of the radio survey. And then as you look to these more classical extended double load FR2 systems, we don't find any difference between the red and the blue quasars. So why is this interesting? These results actually rule out the simple orientation model alone and suggest there's some more fundamental differences. So we don't believe red quasars are just normal quasars seen edge on. So why is this? So if you imagine a blue quasar, you're looking more face on to the quasar, you might expect blue quasars to have enhanced radio emission because you're more along the line of sight to the radio jet, and so you get Doppler boosting. But the fact that we see the exact opposite tells us there's something more special going on in these red quasars. So our kind of toy model that we're working on at the moment is something that looks a little bit like this, where we have red quasars are in this kind of dusty phase, and then they either have these strong winds or these compact young jets that are causing shocks in this dusty ISM. And these shocks cause this enhanced compact radio emission. But this is just a model, so we need to go on to test whether this is actually makes sense. So since this initial study, we've had a lot of work out, mainly in the radio, and I've just listed some of the papers here that have come out from our group. So if you want to know more, then I encourage you to read any of these. But I'll just briefly talk about a couple of the key results that have come out of these subsequent papers. So this plot here was taken from a summary paper that I wrote last year on the radio properties of red and blue quasars. And this plot is showing the fraction of radio detected red quasars divided by blue. So essentially the radio detection enhancement of the red quasars. And then on the x-axis is radio loudness. And just to note, in our studies, we define radio loudness a little bit different from the classical definition. We define it as a ratio of the 1.4 gigahertz luminosity to the 6 micron luminosity. And I believe the classical definition is more like 10 gigahertz to B-band optical luminosity. So the reason we use the 6 micron luminosity is because this is less affected by extinction than optical luminosity. And then in the different colors here, in the orange is first. So this is updating Lizelka's work, but now to DR14. In the blue is from a paper I wrote in 2020 that combined 2 high resolution deep radio surveys, one in Stripe 82 and one in Cosmos. So very deep data, but limited on source statistics. So that's in blue. And then in pink is the LOFAR LOTS DR1 144 megahertz study that David Rosario wrote in 2020. And in our definition of radio loudness, the radio loud, radio quiet threshold roughly corresponds to -4.2. So what we find in all 3 of these surveys is that the red quasars show an enhanced radio emission around this radio quiet threshold. So around -5 to -4 in this radio loudness parameter. And then we see it decrease both at the extreme radio loud and radio quiet end. And this isn't exactly what we were expecting to see. So in my 2020 paper, we tried to work out why do we have this decrease at this very radio quiet end. So to do this, we used the multi-wavelength data available in Cosmos and actually tried to distinguish between sources that had their radio emission dominated by star formation or by AGN processes. And when we do this, although we're very limited in source statistics, it looks something like this, where the green points correspond to the sources that have radio emission dominated by AGN mechanisms, and this black point is star formation. And although the error bars are quite large, what we find is that those that have radio emission dominated by star formation processes don't show an enhancement. It's consistent with unity. So what we think is happening is as you get to more radio quiet systems, your radio emissions getting more and more dominated by star formation. And because we don't expect any differences in the star formation properties between red and blue, which I'll go on to in a sec, this means that the radio enhancement is essentially diluted by star formation. So we think the radio enhancement is due to some kind of AGN mechanism. And just to note, in Gabby Calistro-Rivera's paper in 2021, she looked at broadband SED composites of red and blue quasars and didn't find any differences in the star formation rates between red and blue quasars, which supports this. And we also have some preliminary ALMA data that also supports this. So going even deeper with this, with the radio data, in David Vizario's 2021 paper, we got E. Berlin observations of 20 red and 20 blue or control quasars that had radio emission that was compact or unresolved at 5 arc seconds, so in first. And we observed that with E. Merlin, which is now going down to 0.2 arc second resolution. So we're actually probing kiloparsec scale, which is roughly host galaxy at these redshifts. And the first thing that we found was the majority of these compact radio sources are still unresolved, even at these incredibly small scales. The second thing we found, which you can probably just see by eye, is that in the red quasars, we find a significant excess in the number of slightly extended radio sources. So here's a couple of examples I'm pointing out. So this is very interesting, and it suggests that the radio enhancement is the radio emissions on very small compact scales, and we think is due to either small scale winds, small scale jets, or winds or frustrated jets that are interacting with the ISM, which is sort of the model I showed earlier. But unfortunately, just with radio morphology, it's very difficult to categorically say which one of these it actually is. So we actually have UGMRT multiband radio data for these sources, where we're going to construct sensitive radio SEDs in order to try and distinguish between these different scenarios. But I don't really have time to go into that, and that's going to be a future paper. So what are the open questions after all of this kind of radio work that we've done? So I just said that we think dust is the cause of the red colors, but there's actually multiple things that can make a quasar look red. There could be host galaxy contribution, synchrotron emission, or just intrinsically red continuum. Secondly, the accretion disk properties different in red quasars, for example, Eddington ratio, black hole mass, because if they are, this could be an explanation of the very different radio properties we see. And finally, can we actually find outflows in these red quasars? So I said that the radio emissions either due to frustrated jets or winds, but is there some other way that we can try and test to see if we see winds in red quasars? And hopefully this is all sort of answered in my next paper that has just been published actually, which is using VLT X-shooter data. So X-shooter is a multi-wavelength medium resolution spectrograph on the VLT. And what's great about X-shooter is that it provides continuous wavelength coverage from 3,000 all the way to 25,000 angstrom. So this is from the UV all the way to the near infrared. So we can get these very broad wavelength spectra. So I'll just jump straight into the data. Here is showing the sample that we observed. So on the top are our control quasars, where we observed 13, but we also included 15 archival sources from Capilupo 2015. And in the bottom are 12 red quasars that we observed. And all of these are, just a note, are in a redshift range 1.45 to 1.65. And these plots are normalized to H alpha. And the bold line over the top is the composite for these two samples. So if you're unfamiliar with quasar spectra, the top here is a very kind of typical looking quasar where we have this rising blue continuum. And then over the top, we have these broad and narrow emission lines. And what you can probably notice in terms of the difference between the red and the blue just by eye is that these red quasars show a spectral turnover. And already this is kind of indicating to us that dust is likely the cause of the red colors, because with dust, you expect this wavelength dependence loss of flux. But obviously we want to actually quantify this. So to do that, I fit dust extinction curves. So I take our control composite, I add some dust, and I try and fit this to the red quasar spectra. And I test 5 different extinction curves: an SMC, a Milky Way law, a simple power law, a flatter curve, and a steeper curve. And the reason I test different extinction curves is because your dust extinction curve can tell you something about the nature and the location of the dust. So very just simplifying things, a flatter curve tells you that you likely have larger dust grains, which means the dust is probably formed further away from the central nucleus, so that the larger dust grains don't get destroyed by the activity in the nucleus, or they're formed in an outflowing wind that's leaving the center quick enough so that the larger grains don't get destroyed. And then a steeper curve, therefore, corresponds to smaller dust grains that are likely formed closer into the nucleus. So this little video kind of summarizes our approach, where in the blue we have the control composite, in red we have our red spectra, and then in gray is the blue composite plus some amount of dust, which is shown in the bottom right. And what we find that is just simply adding some dust to this blue quasar, we can actually recreate the shape of the majority of the red quasars. So we find that our red quasars are fully consistent with dust reddening. And just to note, these are very modest amounts of dust. We only find an AV of 0.1 to 0.6 because these are optically selected red quasars. So these are not these extremely red, very heavily obscured systems. So do we find a difference between the different extinction curves? Short answer is not really. We don't really find any particular extinction curves favored, but we can rule out the Milky Way and flat curve, as these don't provide a good fit for the red quasars. And this plot here is showing extinction versus G minus I. And if you remember, that is what we select our red quasars on. And we can see this quite nice correlation, which tells us our method of selecting red quasars is robust. Obviously, we don't have a huge sample here, so what I would love to do is actually expand our sample and really see, do we find a difference in extinction curve with increasing redness? But that, again, that's something for the future. So looking at the accretion properties, we fit just a simple thin accretion disk model to both the red and the control. We fix black hole mass, which we estimate from the H alpha line through spectral fitting, but I don't have time to go into that. And also extinction, which we get from this extinction curve analysis. We then leave spin and mass accretion rate as free parameters, and then fit the spectra. And what we find is that the majority of the red and the control are fit very well with just this very simple thin accretion disk model. And we don't find any significant differences in the accretion properties, so spin and mass accretion rate. We also reran this analysis, but leaving extinction as a free parameter. And we found that the majority of the red quasars needed similar levels of dust extinction to what we estimated from our continuum analysis in order to produce a good fit. So we don't think there's any difference in significant differences in the accretion properties once accounting for dust. And this is just a little example plot of a red quasar which has been de-reddened in order to fit this accretion disk model. And then finally, do we find winds in red quasars? So two ways that you can search for outflows in quasars is to look at blue shift or broadening of certain emission lines, for example, O3 and carbon-4, the two main ones that are used. So we have a look. We don't find any strong evidence for broader or blue shifted O3 in either the core or the wing components. So what I mean by this is here are all the red and all the control with the fits. The overall fit is in blue and then the different components in red and green. And what you can probably see is that there's a number of very strong and very broad O3 in both the red and control, but we don't find a higher incidence in the red quasars, although we are limited on source statistics. We find tentative evidence for larger carbon-4 blue shifts in the red quasars, but this isn't statistically significant. So ultimately, we need a larger X-shooter sample in order to robustly test these differences. And we did get time awarded last cycle, so we're hoping to expand on this sample. So just brief conclusions. We find enhanced radio emission in red quasars on kind of nuclear to galaxy scales. We find dust is the main cause of the reddening and don't find any significant differences in the accretion properties between red and typical quasars. We don't find any strong evidence for stronger outflows in red quasars, but we are limited in source statistics. And I just want to note, if you want to look at our X-shooter composites or that dust movie that I showed, they're both available on GitHub using this link here. So I just want to take a couple of minutes just to kind of talk about what I want to do in the future. I've already mentioned our GMRT data that I'm hoping to produce and have a look at. I'm also quite heavily involved with the Dark Energy Spectroscopic Instrument, or DESI. And within DESI, I have a program which is trying to select dust-obscured quasars that might have otherwise been missed by the nominal quasar selection. And this uses a target selection based on WISE infrared colors. And as Paul mentioned, I have just accepted a PDRA position at Newcastle University, where I'm going to work on MOONS, which is the multi-object optical and near-infrared spectrograph. So very similar to kind of DESI and my work with X-shooter. And I just want to end on a little kind of tease of what I'm working on right now, which is looking at my DESI program. So here I'm just showing some composites. So in black is just a DESI quasar composite. In red is a red SDSS composite that we created. And then a very, very preliminary in this dark and maroon color is what we have so far from our DESI red quasar program. So you can see that with DESI, we're pushing to much more obscured systems than what we can find in SDSS, which is really exciting. So thank you very much. I'm happy to answer any questions.
Thank you so much, Vicky, for the really amazing talk. So I would also open the floor to questions, either online or here in the Zoom. Yep, maybe Giacomo, you may start the question.
Sorry, thank you, Vicky. Really fascinating. Just again, not at all my topic, but I was wondering, when you see this difference, this red and typical quasars, is there any chance that this is due to a different environmental effect? I don't know. You see what I mean? The red. I don't know. Do you see something in the red that pop up in terms of environment where they are?
I guess it depends how large you're defining an environment. We had a study where we looked at halo mass of red and blue quasars, and we don't find any significant differences. Whereas with obscured and unobscured, there are studies that do find differences in the halo mass, but we don't find any differences on the very large scale environment.
Okay, so because I guess, I don't know, but to go to that, to the very center, I mean, close to because to affect the disk, that's what I mean, it's difficult to I don't know, to see an environmental effect to such small scale, I don't know, with respect to the structure of the galaxy itself, or I don't know. Yeah, right, that's the point. Yes, so it's something internal, it's something, what's the physics that generates that? That's the question, basically.
So I guess we're not too sure. We're seeing, that's kind of what we're looking at now. We see some interesting differences with the carbon-4, which we don't really understand yet, but it's kind of telling us that maybe the differences, or at least the scale of which something interesting is going on, is quite small scale. And I guess that's all I can say at the moment, because we're not completely sure. We also find an interesting link to broad absorption line quasars, so quasars known to host very powerful outflows. We find some interesting differences in both the radio and the reddening. So again, we're not sure whether a similar kind of mechanism that produces these bow winds is also what is producing maybe a slightly weaker wind in a red quasar that is also producing enhanced radio emission. But I guess that was a long way of saying we're not completely sure yet. We're still working on it.
Okay. Thank you very much. Thank you.
Yep. So I also see there's a question by Ash from the Zoom chat. So maybe I will speak out the question for her. So he says, thanks, Vicky. Really nice talk and interesting results. I have 2 questions. Firstly, do you maybe cross-check the dust content through Balmer decrement to see if that predicts similar results for the red quasars having higher dust? Secondly, were the full half max also consistent for the emission lines when comparing the red and control samples?
Okay, so, well, that I think I have as a, sorry, I have too many extra slides. Yeah, so we did look at the Balmer decrements. This is kind of the plot that's in the paper where, so for those that don't know, the Balmer decrement is the ratio of the H alpha flux to the H beta flux. And we took the broad line Balmer decrement, and then you can change that into an extinction using this law by Calzetti. And this is what we get, where I have Balmer decrement versus extinction that we get. But extinction we get from the continuum, and then I've changed it into extinction over here. And our composite is in the blue line here, and the intrinsic scatter, because the problem with Balmer decrements is quite a lot of intrinsic scatter, is shown by this blue. And here is a zoom in. These black points are kind of heavily reddened quasars from the Glickman first 2-mass sample. And what you find is that we do actually find red quasars show higher Balmer decrements, especially in a number of upper limits, due to the fact that the H beta was so suppressed we couldn't actually measure a reliable H beta flux. We only got a H alpha flux. But we also find that majority are within the scatter. So they do agree in a sense, but because there is just a lot of scatter in Balmer decrements, it's difficult to say too much about it, which is kind of part of the reason I didn't really show this plot. But you do find higher Balmer decrements in the red quasars compared to the blue on the whole. The second question about full width half max of different lines. I'm not exactly sure what you meant by that question. We looked at the full width half max of the O3 in order to look for differences in the outflow properties. We also looked at O2, but unfortunately that was in a atmospheric absorption zone for our sample. But I'm not sure about other emission lines, or what you would. Is it just whether there's a difference, I guess, in the full width half max?
Hi, Vicky. Thanks a lot for the talk. I can clarify a bit. I think I was actually also looking to see if the red quasars would maybe have stronger outflows, or are they having similar outflows by actually looking at the FWHM.
So we don't find any significant differences in the forward path max of the O3 lines or the carbon 4 we also looked at. So I guess no, the answer is no, but the strong caveat is we just don't have a very big sample. So I would love to kind of redo this analysis with a much larger X-shooter sample. That's the hope.
Thank you. That explains it very well. Very nice results.
Thank you.
Yep. So thanks, Ash, for the questions. And also just to see if there's any more questions from the Zoom or from YouTube. And maybe I also chip in for my own questions. So I have this naive question because I always think back when you mentioned this may not be due to orientation problems. But as we know, the orientation itself also, because as we observe, this will actually affect the dust properties as we see. So I'm not sure if there's any say from the modeling side saying like if you have different inclination of this quasar, how would that actually affect the spectrum, etc., in the simulations, and that we're able to shed some light on these questions overall. I mean,
that's a very good point. I hadn't thought of whether the orientation affects the dust properties. I guess with all of this, it's a little bit tricky because when we say that there certainly will just be red quasars that are red only due to orientation and are just no different from blue. But we think that the kind of the special population is what we call it, that show these peculiar radio properties are the ones that it's not just orientation, they might be in this different evolutionary phase. But no, I'll definitely have a look at that to see if there is some way to predict that. Yeah, that would be good.
Yeah, but yeah, because I'm not in the field, but just this very naive thought on this. So, and also and the second question correctly mentioned is, do you think in near future with the even higher resolution, do you think we can even zoom in to better probe possible smaller scale outflow from the red quasars or not?
So something I would really like to do is to get VLBI data or certainly in the future even high resolution on those email sources to zoom. Can we basically zoom in far enough that we can start resolving things? I guess the problem is that it's really, I've been talking to people that work in radio and they said it's quite difficult to categorically, even if you see something that looks like a jet, it's difficult to know for sure that it's a jet versus a wind. I think if you see something that's very collimated, then you would assume it's a jet, and if it's something a bit more fluffy and dispersed, you'd assume it's a wind. I don't know how robust you could just be on wind versus jet just on morphology. But yeah, we certainly do want even higher resolution to at least just get a kind of handle on the exact size of these things, instead of just all these upper limits that we have at the moment.
Yeah, thanks so much, Vicky, again for that. So since I don't see more questions from YouTube or from the Zoom chat, then I will pass back to Giacomo.
Yes, thank you. Thank you, Paul. Congratulations again first, thank you to Paul for chatting. Very good. Thank you very much. And also congratulations again to Victoria and to Andrea for the great talks, and congratulations for your career and good luck for the upcoming months. All the best, and wish you to see you again. The next event is going to happen on next week. As I said, all these videos are available on YouTube. There is a playlist where you can watch also the other talks, and also please don't forget to look at our web pages where there are all the talks available and the CVs of our educated scientists. And also you can download the booklet of proceedings of last year, and remember there will be a book for proceeding for this year as well, so you can also see that. With this we can close. Thank you very much and see you next week. Bye bye.
Bye bye.